Okay. Hi, everyone. My name is Nick, and today I'd like to teach you a little bit about raw WebGL. So kind of in a nutshell, what we're going to be doing with WebGL is we're going to be describing a bunch of points somewhere in space. We're going to use some math maybe to spin them around and transform them. And then we're going to draw a bunch of triangles between all these points, and we're going to put that up on the screen. So really quickly, I'd like to see a show of hands. How many people here have tried Three.js? Awesome. Okay, and keep your hands up. For people who have tried Three.js, how many of you have ever handwritten your own shader? Okay, so for everyone else in the audience, this talk is for you. So just a little bit of a warning, there's a lot to graphics programming. It's one of those things where you start learning about it, and then there's like, hey, there's another whole book you can go read about it. And so this guy, Fabien Seglard, has this great website for book recommendations, and so it's like this rabbit hole that like you kind of read another book, and you're like, oh, great, there's another book I have to read. So be careful, a warning, it's dangerous. If you find this interesting, you'll probably end up going off the deep end with it. And so with graphics programming, we end up doing a lot of math, right? There's a lot of physics. How do we accurately like model this phenomenon that I'm witnessing? But then for the real-time aspect, it's a lot of the computer science is how do I compute all this math fast enough to still hit my target time to render or frame rate? And so one of the things that I tell people all the time is that graphics programming is really all of the math that you learned and you always wondered in school, like, why was this useful, right? And it becomes immediately clear when you start doing graphics programming. It's a lot of geometry, a lot of trig, and a lot of linear algebra, a lot of matrix math. So a little bit of history, there's this separate organization called the Kronos Group, and they are a chair of these kind of cross-platform APIs for both like operating system vendors and hardware manufacturers to create this API called OpenGL. There's an embedded standard, which kind of gets rid of a lot of cruft, and WebGL, which is a safe, more portable format than OpenGL-ES. And so there's a little bit of the timeline and how they're all related, I guess the family tree. So this diagram is the OpenGL-ES 2.0 programmable pipeline, which WebGL shares. The exact details of it aren't the most important in my opinion, and I think other people elsewhere will cover it better in more depth. I think what's more important to know about this is not too long ago, this entire process was implemented entirely in hardware. It was called the fixed function pipeline, and you had kind of no control. Like you could feed it data, but after that, it took care of everything. And so a lot of people working in real-time graphics wanted to have more control over the rendering process. And so these two boxes here, the vertex shader and the fragment shader, those are now, you're able to program them in software using these tiny programs called shaders. And so that's a little bit about what we're going to cover today. So what goes into a WebGL application? What do I have to worry about? You know, as a web developer, I have to load assets, right? But what kind of assets do I deal with? And so if you look at the list, you can kind of break it down into three major categories of there's shaders, buffers, and textures, where your shaders are the sort, you can treat them as giant string literals of the little program you want to run. Buffers can be vertices, your camera position, your light position, colors, generic data, right? Anything you put in a buffer. And textures are mostly bitmaps, but they can also be videos or even buffers of data themselves, right? So all of these things are optional except for the shader, a single shader pair. You need at least one to start rendering things. Even then, you can get away with no shaders, but all you can do is clear the canvas, so it's not terribly useful. So I'd like to cover some of the terminology I think is really helpful to establish a baseline. So we'll start off with a vertex, right? It's just kind of like this point somewhere in space. And if we take a bunch of these points in space and connect them all, we wind up with a polygon. And if we have a bunch of these polygons, we wind up with a mesh, which is sometimes also referred to as a model. If you see someone referring to their model and someone else in another article is referring to a mesh, they're talking about the same thing. So, but one of the things that's interesting, if you notice in this mesh, is a lot of these polygons in here are triangles. And think about it for a second. Why would it be useful to use triangles as a primitive as opposed to a square, which is called a quad, or maybe a more complex polygon? And the reason why is if you have 3 points, they're always guaranteed to be coplanar. They're going to lie on the same two-dimensional plane. Whereas if you have 4 points, you can think about if you had these 4 points and you were to twist some of them, there's no way to guarantee that they can all be coplanar. And the reason why that's important is that's going to allow us to do a lot of very fast math using matrices later on. So a buffer, I honestly think of D flip-flops, but they're pretty much used for kind of storing data when 2 different things are communicating and maybe at different speeds or different rates, right? But you can think of it maybe as just an array and typically like a typed array. And then we have transformations, right? There are many different kinds of transformations, and what's important to know about transformations is that they preserve parallel lines. Things like angles will change, distances, but ratios and things that are parallel will stay like that afterwards. So kind of the 3 basic ones and how we represent them using matrix math, we start off with translation, and here you can see the transformation matrix that we would use. There's rotation and scale. And one of the things that's very interesting when you start looking at these vertices is you would think they just have an x, y, and z coordinate, but they also have this 4th dimensional component called a w. And it's really weird, and it's kind of hard to explain. They're called homogeneous coordinates. And the reason why we use them in 3D computer graphics is it allows us to represent distances that are near infinite. So after this homogenization process, we end up dividing each x, y, and z component by w itself. And so as w approaches 0, the x, y, and z components will end up approaching infinity, which is very important later when we start doing calculations related to perspective. And it also allows us to represent our transformations as a series of composable matrix multiplications. And so if we go back and look real quick, scaling, this could absolutely be done with a 3x3 matrix. Rotation could be done with a 3x3 matrix, but translation cannot be done with a 3x3 matrix. So that's why we need to use 4-dimensional coordinates in order to make a series of transformations, matrices that can be combined. So perspective is a very interesting kind of illusion that we see where if you take this picture, for instance, this is a street with trees lined it down the whole length of it. And let's just assume that the trees are all the same height. Well, what's weird is trees that are further away appear shorter, and the ones that are further away also appear closer together than the ones that are close by. So what we'll end up doing is a little bit of math to kind of take things that are farther away and squish them down and bring them inwards a little bit. An interesting shape when we start talking about perspective to know about is called a frustum. A frustum is essentially a pyramid with the top lopped off. And when we start thinking about the field of view, we wind up with a shape called the viewing frustum, right? It has a top, a bottom, a right, and a left, and a near and a far. And maybe in one of your video games, you've been playing with the video settings and you increase the draw distance. All that simply is doing is increasing the depth to that far viewing frustum, right? And so more things are rendered inside of it. And what's important about this shape is what we're going to be doing is drawing points. And if any of the points are outside of this, they're not going to get drawn. The graphics card's not going to waste processing power or time on drawing triangles within these points because they're off stream. They've been culled. So a bitmap is just like your PNGs, your JPEGs is a simple listing of your RGB alpha values, maybe encoded in some other format, but once it's decoded, you wind up with a bitmap. A texture is simply using one of these bitmaps and applying it or mapping it onto one of your meshes or models. Sampling is a way for us to kind of help. It's an approximation, right? So with real-time rendering, you'll start seeing lots and lots of approximations where we can't always get the correct answer, but we can do with a less perfect answer because it allows us to calculate it much faster. And so sampling is the act of essentially allowing us to approximate an integral really, really quickly, right? So let's say that the orange curve here was our actual signal? Well, if we take one sample and kind of assume that the rectangle underneath, the area underneath that point, is the amount of light that reached our shutter in a certain amount of time, that allows us to approximate it really quickly. Now, you can see here there's points where we're kind of guessing a little less on the low end and some where we're a little high. So it's not perfect, and you can take more samples, but sometimes sampling can be expensive. So there's lots of different techniques for sampling that I won't cover. And the scary sounding term rasterization is literally just a form of sampling. A fragment, which are important when we get to fragment shaders, they're like a subset of a pixel, but they store lots of different information. They're more of like a data structure, right? And so if we assume that these blue boxes are pixels and the orange dots are where we're choosing to sample within a picture, and we have a primitive, like our triangle in green, and anywhere where we have a hit from the sampling process, we wind up with this polygon that's kind of a combination of the bounding box of the pixel and the primitive itself. So when we start animating, right, we're going to have many, many frames animating, and a moving picture we can assume is a multiple moving images, right? And if we think of it that way, then a frame is just one. So when I start talking about we're going to render a frame, this isn't a full second of animation. It's just one individual still image. So what is real-time rendering? What makes real-time rendering real-time is the sense that we do all of our update and render functions fast enough that we can take into account user input. And so we have to take lots of shortcuts in order to kind of meet that goal or that deadline that people who do offline or pre-rendered graphics, they don't really have to worry about. And so for 60 frames a second, we only get 16.6 milliseconds to kind of compute and render our scene. It's actually a little bit less than that in a browser because you have to worry about the compositor. So those are very tight deadlines that you have to kind of render an entire frame. And so pre-rendering, right? I always think of like these Disney and Pixar films. It like blows my mind to know that Pixar, even with a massive server farm, it still takes them on average 7 hours to render an individual frame. That means that 1 frame has, 1 second is typically has 24 frames in it. And so that means that to render about a second of video takes about a week. And at most 39 hours, which is mind-blowing. And so we need to be able to do our calculations much, much faster than that, but we can't always meet the same quality that you have in pre-rendering. So shading, both of these cubes on the right and the left here are white cubes. Now, if you hold a white cube in your hand, how do you know it's still a cube, right? You look at it, and usually the shading, or how light falls across a surface, gives you visual cues of where the edges are. And so on the left, we have a cube that would be essentially perfectly lit, right? Like if lights were hitting it from all directions evenly, you couldn't really tell where the edges are. But it's not always accurate you don't always see a cube perfectly lit. So that's what we're doing here with shading, is we're varying the shade across the surface. And a material is just a pair of these shader programs that kind of describes how a material, or how an object will end up looking when shaded. So shaders are little tiny programs that run massively parallel on your graphics card. For today, they come in pairs. OpenGL, the newer editions, have things like compute shaders and geometry shaders, but for now, WebGL just has a vertex and a fragment shader, and they always come in pairs, so we're only going to worry about those. A vertex shader can feed data into a fragment shader. So they don't have to communicate, but there are methods of communication between them. What's really cool about shaders is they can be mixed and matched. So for instance, when I wrote this talk, rather than rewrite all my shaders from scratch, I kind of went into one of my directories that I have all my shaders in that I've written in the past and just looked for and found ones that I had already written and was able to reuse them, which is really cool. So as long as the shaders have kind of the same definitions on outputs and inputs, you can link them together and reuse them. And so what's important to know is that vertex shaders run once for each vertex, And fragment shaders run for each fragment. And what happens is that color values get interpolated between them. And we'll see that a little bit later. One of the things that's very important to know is always know your coordinate system. Canvas 2D and the DOM both assume that the origin is in the top left, and they go down into integer values, right? But Canvas 3D is much different. It assumes the origin is in the very center of a cube, and that positive x is to the right, positive y is up, and positive z is out of the screen. And all of those values are floating point values between 0 and 1. And on the other side would be -1. So we wind up with a 2 by 2 by 2 cube. And any vertex that lies outside of this cube gets culled. It doesn't get drawn. So one of the most frustrating things in graphics programming is the very first time you try and render something and nothing shows up on screen, and then you end up doing out some of the math, and you go, oh, well, one of these vertexes has the x coordinate is 1.5, so obviously it's not going to get drawn, because anything greater than 1, less than -1 doesn't get drawn. And now texture coordinates have a third coordinate system. The coordinate system is sometimes called UV coordinates, but WebGL and OpenGL, the family uses ST, they call them. But what's really great about them is that they also go from 0 to 1, and you can change out the dimensions of your image or use a different image, and it's always 0 to 1. So it makes mapping pretty easy. One of the things that's important to note is most bitmaps are actually stored with the vertical axis flipped, like using the same DOM coordinate system, so we have to flip them. Another thing that's interesting is that there's an API called read pixels, where if you want to read the individual color at a certain point, it actually uses this. It assumes the origin is in the bottom left, which is different than the DOM. So if you want to do something like an on-click handler, you actually have to do math to flip the Y coordinate before you end up reading them. So that's just something to be aware of. But so now with a lot of code, I understand it's probably might be difficult to read, so all of my slides are going to be online. I'm going to tweet a link after this. But we're going to start off with a reference to our canvas, right? And make sure our browser supports canvas. Then we want to try and get a WebGL context. And so we need to call getContext and pass it the string literal either WebGL or experimental WebGL. So I talked about the Chronos group earlier. WebGL is a trademark of theirs that they use to kind of set a minimum bar of quality for WebGL implementations. And so for instance, on desktop Firefox, we've been certified as WebGL compliant, and so you're able to call getContext and pass it WebGL. Now on Firefox for Android, mobile drivers all over the board, and so it's very hard for us to be able to say that WebGL will work everywhere, and so you need to pass it the string experimental WebGL. So that's a little bit about why some browsers have one or the other, is they may still be working through the certification process with Chronos. So the first thing we want to do, right, once we have a reference to our canvas and we've created this GL context, is we want to clear it. So the first thing we need to do is maybe change the default clear color. So these are floating point values between 0 and 1 for RGBA. So I'm just setting it black, and then you call gl.clear, and you pass it in enum. This is gl.colorbufferbit. Now, if you were to log the actual value of gl.colorbufferbit, you wind up with some like hexadecimal value. Now, OpenGL is a C-based API, and it's very low level. So we're going to see a lot more enums, but you pretty much don't really have to worry about too much. It's just a way for us to kind of do bitwise functions really quickly. So a super underwhelming example, right, is we have a canvas element, and all we're doing is getting a reference and clearing it. So like I said earlier, we need at least one shader pair in order to start rendering. So our very first vertex shader we'll use, we start off with an identifier, a position, right? Like if you said var a position. But we'll notice that there's kind of like two type qualifiers in the shader language. We have an attribute and a vec4. So vec4 is what I think of the actual data structure. It's a vector of 4 floating point numbers. An attribute is kind of defines whether or not it's an input or an output. And I'll cover them in the next slide, but essentially an attribute means it's an input. And so we always have to define a main function, which gets run for every vertex. And there are these magic variables that we have to assign to. Like the goal of the main function is to assign these variables. So the more important one is GL underscore point size, GL underscore position. So what we're doing here is we're saying we're going to pass in a position and just assign that to GL position, which is going to end up telling the graphics card where to place that vertex in our scene. And GL point size is how big of the point do we want it to be drawn. And then in the fragment shader, we end up telling the GL state machine how much precision to use for floating point math. So there's this qualifier precision, medium P float, and it is possible to use higher precision, but for mobile, you should really stick with kind of medium precision. We have another uniform of vec4 called uFragColor, and in the main function of this, of a fragment shader, the goal is to assign GL frag color. So we just take in an input, uFragColor, and we assign that immediately to GL frag color. And so this language that this is written in is called GLSL. There's variants, like if you write graphics code for Microsoft's Direct 3D, their shading language is called HLSL, and there's other ones as well. So attributes and uniforms are both inputs, but like what's the difference between them? What's important is uniform. Think of like the word itself, uniform, is nothing is different here. All the data is uniform. And so uniforms explicitly are the same for all vertices or fragments even. Whereas attributes are unique per vertex. So sometimes we want to have data that all the vertices share, and sometimes we want to have data that only a vertice has access to. What's important to note is that attributes are only available inputs to vertex shaders. They're not available in a fragment shader, whereas uniforms, you can access them in both. And then the communication channel, there's the third type. Besides attributes and uniforms, there's also something called varyings. And so it depends whether you're in a vertex shader or a fragment shader as to whether it's an input or an output. In a vertex shader, it's an output. In a fragment shader, it's an input. And that's the channel they have for communicating between one another. So the first thing we need to do is compile the shaders. And so here what I've done is just written a helper routine, because you end up kind of running similar code to compile both your vertex and fragment shaders. This is going to catch any any lexing or parsing errors that you may have in your shader itself. So what we're doing here is you need to call into your context, you need to call create shader and pass it an enum, either GL vertex shader or fragment shader. You pass it the string literal of your source, and then you call compile on it, and then finally you want to call into the GL state machine and check and see if there is any error, right? Any lexing or parsing errors. So I recommend, as you're going along learning this stuff, writing it by hand, take code and dry it up, right? Don't repeat yourself. Put code that you write commonly, start writing your own library of helper functions and start putting them all together. So once we've compiled them individually, we need to link the compiled vertex and fragment shader together. And so another helper routine that I've written, link, right? We call gl.createProgram, right? A GL program is the linked set of vertex and fragment shaders. We attach both shaders, and then we call link and check it to see if there's any link errors. So maybe we just declared some varyings in one that weren't available in the fragment shader, for instance, and this is the step that will catch the errors. And also this will allow WebGL and the browser itself to kind of get these references into the address space on the graphics card for where these uniforms and uniforms and attributes actually are, for us to pass information into them. Oh, and what's interesting is a 3D application typically will use multiple GL programs. You can use one if you only have like one type of material, say, in your scene. But for instance, the Unreal Citadel demo, right? It has like a castle, and the castle, like the brick, might be one shader program, and then they'll swap that out and use a different one for like the flags flapping in the wind, or another one for the fire, or a whole bunch. So typically 3D applications will have multiple GL programs, and you can kind of switch between them, which is what this gl.use program call is at the bottom. So now in JavaScript, how do we pass data into these small programs running on the graphics card? So we need to get the locations. They're essentially, you can think of like within the browser itself, they're going to have an array of addresses into video memory of like where does data need to go in order to be uploaded. And so in JavaScript, we're just concerned with like what's the index into that array. And so when we call gl.getAttrib location or getUniform location and pass it the program in a string literal of the identifier that we would like to pass data in as, we get back a number that's an index into a vertice for the WebGL state machine. So one of the things that we can do is set these uniforms and attributes directly in JavaScript. There's this whole family of functions. You can see here there's gl.vertexAttrib2f. What that means is besides passing in the location of that identifier, we're passing 2 floating point values. For uniform underneath, I'm calling uniform 4f. That means I'm going to be passing in 4 floats. There's 1f, 2f, 3f, 4f. They all have a fv cousin as well, which is instead of passing individual values, it takes a float 32 array. There's also 1i, 2i, and so on for integers. And Booleans as well, I think, get passed in as integers. But so once we've kind of passed in this data, we want to draw. And so we call gl.drawArrays, and we pass it this enum of the mode. So starting off, let's just draw a couple points on the screen. And we have a first in account in case you don't want to draw all of your data. So super underwhelming example, we're just drawing a single point. If we take a look at the code for this, you can see this is the last time I'm writing this without helper functions. I'm writing my shaders in line as a giant string literal, which has its pros and cons. I like to separate my concerns, so I would rather throw these in files and load them asynchronously versus XHR. But compile either of them, link them both together, say we're going to use this program. Then we need to get the locations of our attribute in our uniform, and then assign them directly, and finally draw them. So I had already alluded to, right, the separation of concerns. But the thing is, we can do really cool tricks by treating these string literals by kind of generating them dynamically at runtime. So maybe you have a dynamic amount of lights in your scene or something. You can, at runtime, ask the user, how many lights would you like to have in your scene? Oh, I will create for you a shader that can handle this and compile it and run it, and stuff like that. So there's cool stuff you can do too. I like to take advantage of reflection, so you can kind of ask the GL state machine, for my active program, how many attributes are there and how many uniforms are there? And then you can iterate over all of them and get their locations. And so typically what I'll do is iterate over all of them and kind of throw them in a uniforms object that's keyed on their identifiers, whose values are their locations, and same thing with the attributes as well. So the same boring example again with code that's been modularized. Here I just wrote a simple function that will allow me to pass in string literals of my vertex and fragment shader. In a callback, I can check if there was any compilation or link errors. Then I say I want to use the program, set the clear color, clear the canvas, and then additional helper functions to get my attributes and uniforms. And then later you can see when I assign to them, I have to go through that attributes object.aPosition to assign them. So let's say we want to draw multiple points. The first thing we'll do is we'll beef up our shaders a little bit. So now, instead of kind of hard coding some of these values, let's make them more dynamic. Let's pass them in through JavaScript. So we'll define an additional, we'll define a vec for the position. We'll change a point size and we'll change a color. So we need to declare 3 additional attributes. But then we want to pass the color out to the fragment shader. So we'll end up defining a varying V color. And what's important in the fragment shader is you'll see we have to redeclare it with the same identifier. Otherwise, we're going to wind up with a link error. So what we do is we pass in these variables and assign position and point size directly in the fragment shader and pass a color immediately through to the varying V color and then assign the varying V color to GL frag color in the fragment shader. So as a naive first attempt, let's use multiple draw calls to build up our scene. So what we can do is kind of define our X, Y, our point size, and our RGB values. We'll iterate over each object in this array, and we'll assign a position, X, Y, and Z, point size, and a color, and then call draw arrays. And if we take a look at this, another underwhelming example, we see here, this is what we wind up with. And so what we're doing is we're actually building up this scene by calling draw arrays multiple times. But the thing is that the draw calls themselves can be very expensive. I've seen many times where the draw call is one of the more expensive calls in the scene. And so the goal is to try and minimize how many times you need to call draw arrays. And so there's a few different techniques we can do there. Like, for instance, one of them is using multiple buffers, for instance. And so another little helper function for initializing a buffer called gl.createBuffer. We check if we were able to allocate the memory for that. We then bind the buffer. So what's interesting, I alluded to that OpenGL and family is a very C-based API. And so what we end up doing with the state machine is we call bind buffer, which says this buffer that I've passed into the call to bind buffer is the active buffer, and all future API calls against buffers are referring to this buffer exclusively. So then when we call buffer data to pass in what would be like a float 32 array worth of data, and then we have to enable this pointer into the data. We need to say that essentially how many elements there are in this buffer itself. So here you can see I'm passing in the number of elements per vertex and assigning them here. And so for instance, for our positions, there should be 2 elements per vertex, right? If we concern ourselves with just XY coordinates, then each vertex gets 1 XY, XY, XY. For point size, there's only 1 element per vertex, as each vertex gets its own point size. And then for color, there should be 3, RGB. But one of the things that's, so if we take a look at an example, right? So here's the same boring scene rendered with multiple buffers. And so what's important here is that we've been able to cut down on our number of draw calls. By using multiple buffers of unique data per vertex, we can then call draw arrays just once. So this is an important optimization to be able to make. But one of the issues, though, is when you start having, whenever you have to communicate from the CPU to the GPU, usually that's a point of potential slowdown because typically they're running at different speeds. And so for them to synchronize, for you to pass data between them is always a form of a bottleneck. So instead of uploading multiple little individual buffers, sometimes it can be faster to put all this data together in one buffer and push one buffer up to the GPU. And so with multiple buffers, right, we can picture kind of 3 buffers, one with XY, 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 one with point size, point size, point size, and one with RGB, RGB, RGB. Or what we can do is interleave these buffers. So we wind up with one buffer which has an XY point size RGB, XY point size RGB, XY point size RGB. And so there's a couple extra calls. First thing we need to do is see how many bytes per element that we have. If we're using a float 32 array, 32 means there's 32 bits. If there's 8 bytes per bit, then that means we should have 4 bytes for a float 32 array. And what we're doing is we're saying an offset. So there's a stride and an offset that you pass to vertex attrib pointer, where the stride is always how many bytes essentially does one vertex get. So the stride for this particular float 32 array is 6, and the offset for the A position is 0, because our position starts at index 0. For the point size, we have the same stride, but the offset is now 2. And for A color, same stride, but now the offset is 3. So again, here's the same example, but instead of using multiple individual buffers, it's using one big interleave buffer. Now, which is better, right? Like everything else, it depends, right? That's the answer for almost everything in graphics programming, right? One of the issues we tend to run in with is what if in our interleave buffer we're mixing kind of static data that never changes and dynamic data? Do we really want to be changing our buffer and re-uploading this one big buffer to the graphics call? So in that case, it might be wiser to use multiple buffers, but keep like static data in one buffer and then dynamic data in its own individual buffers. That way, when you do have to communicate with a GPU, you're not sending it more data than it needs. So again, profile, and it depends on your situation. And there's other tricks that I won't cover today, but there's things called element array buffers that allow you to represent duplicate data using array indices, which can help you cut down on the memory requirements to represent your meshes or models. So up to this point, we've just been drawing points, right? Like I haven't been showing off any like eye-popping WebGL demos because I really want to send home the message that we're just dealing with vertices here, points in space that we're going to spin around and move around. And so when we call GL draw arrays, I've been passing the enum gl.points. But what's really cool about your scene is that you can change how it gets rendered. And we've just been drawing points, but there's other modes such as lines and triangles. And if we take a look at the example here, what I'm doing in the code is I'm just like duplicating a lot of data, but I have an array of all the different modes, and I'm iterating over all of them and drawing them with a different mode. So the first example you can see here, this is drawing them as points. Lines takes pairs of points and draws lines between them. Then we'll skip drawing the line between the next vertice and do the next two. A line strip will do a line between all the vertices. A line loop is the same as the line strip, but we'll connect them again at the end. Triangles takes individual groups of 3 vertices and draws individual triangles between them. Triangle strip will reuse the 2 vertices of the last triangle. So you end up with a triangle between V0, V1, and V2, but then the second triangle is between V1, V2, and V3. And then finally, a triangle fan always reuses a vertex 0. So here you can see a triangle between vertex 0, vertex 1, vertex 2, and then vertex 0, vertex 3, vertex 4. So in order to render things with a correct perspective, that looks correct based on our human visual system, we need kind of 3 things. We need a model matrix, which is essentially the composition of all the different transforms we want to do. So for instance, like an artist, when they render this dolphin, they might assume they have the full clipping space to work with, but you don't want your dolphin to take up the whole screen, so you're probably going to shrink it down and rotate it around, right? So that's your model matrix. And then we need a point and 2 vectors which we can then put into a matrix to represent our view matrix, or maybe you can think of it as a camera a little bit. So relative to our scene, we need a point in space. Where am I relative to my model? I need a vector, what direction am I looking in? And then finally, I need an up vector, which vector is up? And then finally, we want a projection matrix. So we want to know what's our viewing angle of the scene, what's the aspect ratio, the width to the height, and how far apart are the near and far clipping planes of our viewing frustum. And so with this example, you can see here what we're doing in code. So my recommendation is, I'm not a huge fan of linear algebra. That class totally kicked my butt in college. But I recommend stick with someone else's library and just use that. So what we're doing here is we're setting up our matrices and just passing them in either as uniforms or attributes. And in Firefox, we can use the shader editor to take a look at our shaders. So here you can see this comment. Matrix multiplication is not commutative. Matrix A times matrix B is not equivalent to matrix B times matrix A. And that will lead you into some frustrating bugs if you ever run into that. But what's important to know about this is that all of these triangles have the same x and y coordinates, just different z values. But the thing is, the ones that are farther back after this perspective transformation, they appear shorter and they appear closer together. So with animation, you're probably aware that in an update or in a request animation frame loop, you're going to have your update in your render functions. So as an example here, we have our triangle now. We're drawing our 3 points, but we're drawing it as a triangle instead of as points. And the color, we can see it being interpolated in between the vertices themselves. So what we're doing here is in my animation frame loop, we have our update. So all I'm doing is saying I want to rotate across the y-axis my model matrix. And I'm not using velocity-based animation. This is just doing 1 radian per second, but you should do velocity-based animation. And then we're passing that data off to the GPU, calling uniform matrix for FV. The V is because I'm passing a float 32 array. And then the render part is we always need to clear the canvas. and then call draw arrays. And you can see I'm using the enum triangles, and then set up our request animation frame again to loop. So for textures, there's kind of two different things that we need to worry about. The first is initializing a texture, and then the second one is actually sampling from what we want to use as a texture. So we need to call gl.createTexture. We should probably check and verify we were able to do that. But what's interesting is the graphics card has these things called texture units, which are like slots that you can reference from in a shader. And there's typically a set amount, a finite amount that you have, but multiple textures can reuse those texture units. It's just whichever texture is the one that's bound is the one that the shader refers to when it tries to access that. So we call bind texture to say all future texture calls are against this texture, and there's a bunch of parameters that we need to set on it. What happens when we need to shrink it or magnify it or minify it, and then what happens on the edges if it doesn't fit, right? And then finally, we need to set a uniform of which texture unit do I actually want to refer to. So this 0 here is referring to this texture unit 0. And then the second part that we need to worry about is the actual sampling. So again, you don't always have to call bind texture. This is safe to do in case you've been doing things with other textures. We want to rebind this one as the active one. We need to tell WebGL to flip the y coordinates typically on any bitmap that we're sampling from, because again, the origin is different. So if you start writing texture code and your texture is upside down, that's why. And then finally, the text image 2D call. This is the important one. It's also a huge bottleneck I see a lot in WebGL programs, is the actual sampling from this bitmap and transferring it to the GPU. But what's really cool about it is that we can pass it a bunch of different things. We can pass it an image element. We can pass it an array buffer of raw bits, at which point you probably don't want to flip it, but we can pass it another canvas element. So if you want to use the canvas 2D API, render into that, and then sample from it, you can do that. Or you can even use a video element, which is really cool. So if you're just using static images, all of this can kind of be done in one function call. But if you're using a video, you have to keep sampling from the video, which can be very expensive. And you might also be limited on your amount of texture units if you're doing things like deferred rendering. So here's an example where on the left we have a video, and on the right we have our same animating triangle, but instead of drawing it as colors, we're sampling from the video element. So we can see down here we have our actual vertice coordinates, right? Minus 0.5 is the bottom left, minus 0.5. 0.5 minus 0.5 is the bottom right. And then 0 and 0.5 is the top right. Those are using the three-dimensional origin system. And then in UV coordinates, we're saying, okay, the first point samples from 0, 0 is the bottom left of this video, 1, 0 is the bottom right, and 0.5, 1.0 is the very top middle here. And so what we end up with is, you can see in the bottom of the triangle, almost the entire of the bottom of the video is included, but at the top, the very corner, the top right and left corners of the video are getting cut out. And so we can play around with that and move it around. But just like a little fun demo is we can use get user media, for instance, to sample from our webcam, right, and do like cool, and sample from that. So again, communication between CPU and GPU can be expensive, so try and minimize uploads. And then finally, the last two things we want to talk about is shading. I'm not really going to cover too much of the code here, but there's two main things to worry about. The first is, what illumination model do you want to use? There's the Lambert, which is cheaper to compute. In fact, it's just taking a cosine of the angle between the surface normal and the light vector. And Blid and Fong, which says, no, there's three different components. There's an ambient, which is light just kind of falling on an object that by being in a lit room. Diffuse light is light falling on it, and then specular, which are kind of highlights. And then there's interpolation techniques. There's flat shading, which each polygon has its own color. You don't really see this too often now because you actually need to upload more data than a fixed function pipeline, but you wind up with these disco ball effects when you try and render a sphere. There's Gouraud shading, which calculates, the colors are calculated per vertex and then passed immediately to the fragment shader, who just kind of assigns them. But you wind up with weird effects called Mach bands on curved surfaces. And then finally, Fong shading, which calculates a color per pixel. But the thing is, the ones that look more technically correct are also much more expensive to render. So I'm not going to cover the code for that. In fact, as of now, you have everything you need to start building abstractions on top of WebGL, right? The basics are just attributes and uniforms. So that's an exercise I'll leave up to everyone here. Some of my recommendations for where can you learn more about this. I think Steve Wittens has this amazing talk, Making WebGL Dance. I think is just so eye-popping and really cool. WebGL 101 by Eric Mahler is a really awesome video on getting started with WebGL. 3-hour-long video, but I highly recommend it. This book, WebGL Programming Guide, a lot of what I told you today is directly from this book. I think that is a really great reference on the raw WebGL API, but it doesn't cover the compiling and the linking of shaders immediately, which is why I think Eric Mahler's is better to start with. Really cool program folks are working on called Shader School, which goes much more in depth into GLSL. The WebGL 2D source is really cool, is how do I implement Canvas on top of WebGL? This book, Computer Graphics Principles and Practice, is really off the deep end into like graphics programming. It's an awesome, awesome reference. And finally, the 3JS source is so fantastic. And so my goal for today was to teach you enough to be able to take a look at the 3JS source and understand what is going on, what is this abstraction doing, and hopefully help you be able to appreciate what it's doing. And another thing I just saw the other day that was really neat was some folks at SIGGRAPH just kind of presented something that they were, I guess I may have closed it, but, oh no, it looks like some folks are even starting to teach university classes with WebGL, which is like awesome for portable real-time graphics. So that's really, really exciting. And there's a book they recommend. I'll have to check that out as well. So thank you very much for your time. I appreciate it. My name's Nick. I'm Lost Oracle on Twitter. I would really love any feedback you have, good or bad. If it's bad, let me know what I could do to improve it. Come chat with us. Everyone at Mozilla hangs out on IRC all day long. I'm \n, which is a valid identifier in IRC. Join the family. You can find me on GitHub and also my blog, where I talk about all kinds of stuff. Oh, sorry, I won't be able to connect. But from assembly programming up to CoffeeScript and graphics and everything in between. So thank you very much for your time, and I'm going to tweet out a link to these slides as a reference. So thank you very much.
Obrigado, Nick.